Hey there, I've got another practice problem for you. This one is off of the 1986 exam, number 78. Number 78. A system consists of two charged particles of equal mass. Initially, the particles are far apart, have zero potential energy, and one particle has non-zero speed. If radiation is neglected, which of the following is true of the total energy of the system? So this is very much a conceptual question. We need to look at the answers immediately before we even do much thinking about the problem. We have to pick the right answer out of these. So we glance at the answers, and then I'm going to kind of talk through my reasoning and why I would pick the one that I would pick. A, it is 0 and remains 0. So we're talking about the energy when it says it. B, the energy is negative and constant. C, the energy is positive and constant. D, I'm going to pull this down, and I don't even know why I'm holding it up. With this blue color, I'm sorry, the printout on this last exam is hard to read, so I'll just read it here. D is, it is constant, but the sign cannot be determined unless the initial velocities of both particles are known. E, it cannot be a constant of the motion because the particles exert force on each other. So this is actually a very simple problem if you fundamentally understand how energy is conserved. And if you're having some issue, any type of issue with this problem, I do have a recommendation for you. And if I ever finish all of these videos on practice physics GRE problems, which at the rate I'm going will be a very long time in the future, but if I do, I will probably write some overall help videos on doing the physics GRE. And one of the sources that I would already say, because I'm reviewing this as a good reference for prepping for the physics GRE, is some books by Richard Feynman. You guys all probably remember Richard Feynman, reading about him in your studies of physics. But I really enjoy his writing style. I think a lot of people really enjoy his writing style. But his notes on physics, I would refer you to. It's one of the first couple sections in those notes on conservation of energy. And he has this description about how all the energy in the universe could be represented by a kid's building blocks. And he describes a situation where you have building blocks and the mom goes in to find the building blocks and the kid hides them in different forms. He hides them in the bathtub, he throws them out the window, etc., etc. But the number of blocks is always the same. And he equates this analogy very well, I think, to conservation of energy. We know that energy changes forms, but overall in the universe, it's a freaking amazing fact that energy is conserved, always. And I think maybe that's not stressed enough in a lot of people's physics courses, just how phenomenally amazing that fact is. And that, for me, helps me clarify this problem a little bit. So physically, I'm imagining these two particles. One thing that they try and throw you off with is they're talking about radiation and charged particles, and that's annoying. But they give you a buy on that. They say that radiation is neglected. And so realize, though, that even if the particles were radiating somehow, the energy would still be conserved. If you counted up the energy that the photons had along with the particles, you would still have the same amount of energy that you ended up with as what you started out with. Energy is conserved. So I want to stress that point. But they give you a buy. They don't even need to be charged particles. That's really just useless information. It as far as I can tell, has no bearing on the problem. I'm trying to think of situations where it has no bearing on the problem. It's going to affect the motions of the particles, obviously, but as far as I can tell, I think about this problem physically, is all of a sudden you have the two particles, and it doesn't matter where they are. It says they're far apart. Are they going to accelerate towards each other or away from each other? Doesn't matter. That would depend on the charge. Right? But what I do know is that if I look at the initial energy of the situation, it's got to be equal to the final energy. the total, and in this case, the way that I see the two energies being represented here is kinetic energy and the potential energy of the particles. In other words, if these particles are exerting conservative forces on each other, they have one potential energy if they're this far from each other, and if I push them together, they're going to have another potential energy. And if I'm just allowing this to move from there to there, it goes without saying their kinetic energies will also be different as well as that motion occurs. But this old, I mean, in my eyes, this is kind of what I'm saying. If this is the kinetic energy plus, can I use P, U? What do you use for potential energy? I forget, U? Let's go with U. This is my kinetic energy initial. My potential energy initial is going to equal my kinetic energy final plus my potential energy final. Okay, it's just, that's bomber proof. You have to realize that that's always going to be the case as long as no non-conservative force is pulling energy out of the situation. So all of that being said, I'm sorry, I'm being very wordy. I could be more concise with this, but I want to make something out of this problem, because otherwise it's very easy. You would have solved this by now if you really knew your stuff. All you have to do is look at the energy that's the initial energy and realize that it will be constant. So at that point, let's see. You've eliminated answer, well, I guess answer E. It cannot be a constant of the motion because the particles exert force on each other. It cannot be a constant of the motion because the particles exert force on each other. I don't even really know what that answer means. I mean, I don't even understand what they're trying to say with that answer. But I'm dissuaded from picking that because it says it cannot be a constant of the motion. And we're talking about the total energy. And I know it's constant, so I can drop E. I feel pretty comfortable dropping E right off the bat. The other ones say that, in not so many words, that the energy is constant. So, is it positive or negative? And that's the other point where you could stumble a little bit. And review your potential energy when you talk about like gravitational potential energy. I need to review, as far as electromagnetism is concerned, what the potential energy is of charged particles. It's not particularly important, even though these are charged particles in this. And if I say this right, I mean, the idea that we always seem to do with potential is we say that it's zero when the charges are at infinity. And then we need to give them a negative potential energy when they move them in from infinity to their positions. That's certainly the case with gravitational potential energy. When the signs, the charge are in there, like I said, I need to review that. I imagine that's probably not the case with charged particles, because due to their charge, positive and negative, one is going to have one charge, one is going to have another one. But it says right in the problem that they have zero potential energy. So in my initial case, going back to this equation, they're giving me this is going to be zero. I don't really care whether this is going positive, whether this is going negative, this term. It's going to be something, but it doesn't matter. What I do know is that this is constant. So that brings me to this. Is this positive or negative? And I'm sorry, I talked for almost 10 minutes here to get to this point, but it's very simple. Can something have, this is just the kinetic energy that we're talking about. Can kinetic energy be negative? We know that the kinetic energy, well, one way of writing the kinetic energy is this. And you always have that V squared there, so you should be thinking in your head, no way. Kinetic energy cannot be negative. It doesn't matter where your vector of that velocity is going. Energy is a scalar, and kinetic energy is always a positive scalar. As far as a student studying for the physics GRE is concerned. So if there's some crazy 0-point energy guy that's going to message in and say, oh, well, kinetic energy can be considered a negative under some circumstances, fine. But as far as I know, kinetic energy is always positive. So we have back to this. This is a 0. This is a positive energy term. I know that the energy is going to be positive, and I know it's going to stay the same. Even if this energy goes down, this energy is going to come up. If this goes up, this is going to go down. And that's, I think, way overkill on this problem. So I'm looking at answer C, being that the energy is positive and it is constant. And that's what I want to pick. So that's it, number 76, 1986. Thanks for watching.